Great. Good afternoon, guys. Can you all hear me? Cool. Great. Thanks, you guys, for coming. I know you guys it's been a busy week. Lots of cool presentations. My name is Troy Gardner. I run a blog at troyworks.com.blog, which covers the insides of ActionScript 3. I'll be talking about advanced state management using a library developed called Cogs, which is a hierarchical state machine. A little bit about me. I'm the director of Flash Interactives at a small startup called KidThing, which is a company that makes children's educational games. And I'll show you a little bit some about the design patterns we're using inside of that application that we built. And I'm hoping to help you guys learn about make interactive projects more successful by understanding state charts, state machines, what they can do for you, in particular nested states, something a lot of people are not used to. And then at the end, we'll cover some of the life cycles typical in our rich internet applications. All the code that I'm going to be showing you, most part, is going to be on the TroyWorks framework, which is on Google Code. I'll talk a little more about the licensing model there. It's an MIT license. You guys can pretty much do whatever you want. Presentation outline is going to be covering what is state, how do you communicate state, how do you implement state, common state patterns, and conclusion. At the very beginning of this, we're going to talk from the very high level, kind of in a very abstract, like if you're in the boardroom talking with clients, how you're going to start thinking about projects in the terms I'm describing. Then we'll start getting into the implementation, which is at the code level, and then we'll start delving back upwards to how you actually use it in applications. So what is state? I'd like to preface this, since this is a Flex conference, the terms I'm using, state and transitions, are different than the ones that Flex actually uses. I like to say that we are compatible with them because those are typically constrained to the view. How do you control what's showing on the stage at any given time? And I'd like to remind you what we were using it first, since this library, the code terminology comes back from the 1980s. One of the things about narratives versus interactives you come across is the cool thing about movies is if you look at every frame, all the state is exposed. You can pause per frame at any point in time and see everything that's available there. That's not so true for our interactive applications. Think about Pac-Man. You could take a video of it, and you would never see some of the bugs and some of the Easter eggs inside of it unless you know the particular code, the combinations of the joystick and the mouse or the buttons to actually reveal them. So if you're trying to figure out what state is inside a particular interactive piece of application, you start to have to look at, well, how would we look at that and start codifying all the different ways? So if we were trying to recreate Pac-Man, a game of it, how do we start deconstructing that? So one opportunity is pointing a video camera at it and then just recording it and starting to see the blur patterns. And this is just a brief example. We can start seeing that the Pac-Man always shows up in the same point in space. We start seeing the ghosts always start from the point in space. That might be one state. It might be the start state. If we do this for any application, we see things like to call traffic patterns. Like here's a picture of a street in a busy intersection. We can start seeing some interesting things that we see lines of cars moving, but there's breaks in the lines. And we see people clustered at this point in time, and then we see some dark spaces. If we're looking at an application at an abstract level of what the user is doing through the system, there's something similar. There's traffic patterns of how the user interacts with the system. There's certain screens they stop on. There's certain transitions they expect in a workflow. If you're looking at state and transitions, anytime you see a stop is our states. So you might notice that even though we can't see them directly, we have a traffic light there because we can determine that based on the breaks in the flow. Similarly, we can see those two flows crossing. We can see there's an intersection there. Those stops are the states I'll be talking about. The movements between states are the transitions. There are some things we're not really that interested in the application. We see that the buildings are always going to be there. We're not really interested in codifying them when we're doing an application. We can also see there's some parts of the daily cycles we don't really care about. Like we could record this for 24 hours and see that Joe in his apartment constantly goes down for coffee every 2 hours because he's a writer and he's on a tight release. We don't really care that, so we toss that kind of state out. So in communicating state, we have this fundamental impedance mismatch between what we're typically given in documentation and what we have to build. So going back to the Pac-Man model, we might get a specification that looks kind of this wireframe. Pac-Man goes here. Some bizarre estimate of like 10 hours how long we think it might take to build something. If we're trying to prototype this, you can imagine that everybody's familiar with Pac-Man. You could create screen comps that represent the game start state, the game, the Pac-Man chasing after you. But to play it is completely different. There's so much that's hidden between the actual screen captures that you're doing. That's why I say things are hidden in time. And even if you get to that point of understanding it, mastery is much, much harder. You could play Pac-Man, you could understand the basic principles, but to actually get mastery of it, it's much, much more difficult. This is why it's hard for people who are doing information architecture to really, truly appreciate what it's going to be like in practice. They have to actually play it to understand that the workflow actually is valid to the user. When you first start getting an interactive project, it's really easy to start with the OOP aspects of the system. And OOP stands for Object-Oriented Programming. And you start thinking about, if you were deconstructing a book, you could look at all the nouns and the verbs of the system. And those are typically your objects that you're participating with. So in this example, we have cats that are animals and they're meows. So if we were creating a class diagram, cats, subclass animal, or subclass animals, and they have certain functions called meow. What I'd like to propose is another terminology called stop-based programming, or state and transition-oriented programming. The states are the mood, the weather, they're always there inside of your system. The transitions are the scene changes in the plot. So using that same example, the cat is alive and it's meowing. It indicates a certain point in time in the application space. State is everywhere. It's in every tier of the model view controller if you're doing interactive stuff. It's in every aspect of design, coding, and specification. It's in every phase of development. It's in every asynchronous call and network communication. If you were to map on one side of this grid all the OOP aspects, the object in your system, your map on the bottom of it, all the states in transition, you would see a projection that your application takes up like a cloud in 2D space or 3D space. I've done a lot of interactive projects, and historically, we don't typically miss the objects in the system. They're fairly easy to identify. There's a person, there's a product, there's a store. But the roles that that person has at any given point in time, like they've locked their password out, those get typically missed, and they have a ripple effect throughout the entire system there. If you get something wrong in the information in the interactive architecture phase, that you miss something in the design element, and that misses something in the technology element, and then you have to go back through and change everything again. And typically this happens pretty close to the time that you're supposed to be deploying this, and causes a lot of frustration. So one of the things you need to do is get designers, architects, and coders on the same page. And for that, it needs a shared lexicon. It gets into how to communicate state. Part of the UML spec is a word called state charts. It was introduced in the 1980s by David Harrell, who was actually, they were designing aircrafts. And you can think of that, you don't want your plane to crash. So if you're dealing with any type of flight navigation, flight simulators, they come up with this terminology to describe how states and transitions happen in the application. These are the basic ingredients, and I'm slightly modifying the UML spec of it to make it more interesting. So states are these kind of roundish blocks, and they're any place along the way that takes it more than a finite period of time. Transitions are between the stops, and they take no time, essentially, from the application perspective. We have actions. These are things that you do along the way. Events, a change of some sort. And in the end, we mix all those together, and we have something that's called a state chart. So we're going to deconstruct the states of a flying fish simulator. And this is the comps we've kind of got from our designer. This is actually one fish, just at different points in time. We've done some time-lapse photography to be able to figure out where the fish is. So how many states do you guys see in this picture? 1? 4? So it's not 100% right or wrong to answer this, but I'm going to suggest that there are 3 steps. Bowl number 1. Bowl number 2, and flying. One of the rules about constructing finite state machines is said that you have to make sure that everything that takes more than a negligible period of time has to have a state of its own. So in this case, it's completely covered. There's really no gaps between the bowl and flying back to bowl number 2. They're crisply defined. You cannot have overlaps between states. So like in this diagram, I have the text overlapping the actual flying state. State machines can't deal with that very gracefully. You contrast this with fuzzy states where at any given point in time, that fish may be a part of any of those sets or have multiple sets. And you can start thinking if you had more than one fish in the system, if that fish jumped from the wet to the dry state, there might be splashes from the secondary fish still in the air that could still get hit by it. So it becomes very, very complicated very, very quickly. And you notice when you get into the state, you start thinking it's wet and it's a % dry. And that's how it lets you know when you start codifying these things as variables rather than states. State topologies have different granularities depending on what you're interested in. So we can imagine if we only care if the fish is playing or not, we might have just a single state, which is useful enough for us. We can also go the opposite end of the spectrum. We can say that fish is on the bottom or the top, or all these different variations. We might normalize it, saying that we only care if the fish is in the bowl, leaving the bowl, or in the air. That might determine the fish's behavior. Transitions are one-way streets between states. So we might start from the bowl number 1, flying. It's fairly easy. We get to bowl number 2. That's pretty obvious from the comps. But it may not be immediately apparent. We might have to go back to the bowl number 1, so we add some other additional transitions. Transition should take 0 time to cross. So technically speaking, the fish has a certain period of time where it's sort of in the bowl and it's half in the air. But from our perspective, it has to be either or. Now that we have all the transitions, we have to think about how do we get to this place how do we get to the scene in the first spot or place? So UML terminology has something called the initial pseudostate and initial transition, which we mark off to the bottom left. Transitions are similar to the laws of physics and business logic. You can't cross between bowl number 1 and bowl number 2. You have to go through the air unless you have a quantum fish which can do these kind of strange jumps. And similar to your business logic, you have to make sure that your state transitions in appropriate ways. If we were to zoom out, we'd see that we exist in a root state. And this is the universe that all the application behavior exists in. Typically, this is sometimes optional when you're just diagramming these things. And we can see the relationship between the pseudostate, which is like the Big Bang of the application. We don't know what happens before the Big Bang, but all of a sudden we are aware that we exist on stage, and then we can start doing things. And similarly, we have kind of the black hole death of the universe of your application. And that's kind of indicated with kind of I look like a drain type of icon. Events are a change in state somewhere. And it's fairly, from my perspective, we're talking about an abstract level of events, not just the ones that you find in the ActionScript 3. In this case, we have the fish suddenly realizing how dismal his life is and decides to do something about it. Events are like food. Sometimes they're consumed, and sometimes they're passed on. Sometimes they trigger an internal response. It doesn't produce an external change. Sometimes they produce a state change, which causes the fish to move someplace else. And that ripples throughout the entire system. State machines also are, your business logic is codified in the actions. So we have basically, we have this in-bowl state. We have the exit bowl kind of actions affiliated when we leave that state. We have these actions which are performed when you enter the air, and then another set of actions which are performed when you enter the bowl. And they're like checklists. You kind of cross them off as you do if you're exiting the bowl or entering the bowl. When we're in a particular state, we may have things which repeat, like breathing over and over again. And at other times, we have single actions, like kick hard when you exit the bowl. As we were to, the state machine would be following this fish going through these different states. It would perform these actions automatically. When we get through describing this problem, we have what's called a state chart, or I prefer the term life cycle because I find a lot of technical people don't really understand what the word state chart means. Life cycle is more approachable. And I like to think of it as a map of the application territory. It's not the actual territory itself, or an application traffic pattern, but not a particular car experience of it. And it's a recipe for project success, provided you don't leave anything out. And you can imagine that users' expectations, if you get the state wrong, they get confused. You get the technology state wrong, you end up with a crashed application. So now that we have this state map, we notice the map is not the journey of a particular user in the application. So this is a map of getting from LA to up here. And on this map, you can't tell where I'm at. So that's really what your application you're developing is really more interested in. There's a terminology called active states. And in this particular case, we have Joe, who is responsible for lighting up the state. When he's in the state, it lights up. And I'm using this kind of visual metaphor to indicate which state is currently active. Inactive states are all the places that Joe is not. And they're non-reactive. I'll get more into that in a second. If we're to model a light switch, this is a state machine for a light switch. It's a simple two-state, two-transition device. States can only be one place at a point in time. You can imagine trying to flick that light switch. As much as you try to get in the middle of it, it's going to flicker, but it's either in the on or the off state at any point in time. The light's going to be either glowing or it's not glowing. Active states receive all the events. Meaning when in the on state, we get anything that happens first, and we don't know what's happening in the off state. So even if state is changing in that room, Joe, the state man, can't actually figure out what's going on until he goes in that room and sees there's messages on that phone. Occasionally, you can have more than one active state at a given point in time, but typically these are orthogonal. They're not related, and they're not kind of bound together. It's like we have two light switches. They're independent in their actions unless they tie to a singular light, like a three-way light switch. Typically, you use events to synchronize them and make sure that they're maintaining state appropriately. Here's an example transition. So we're currently in the on state. We see the event to turn off. We notice that we have an actual transition name turn off, so we're going to take that. We notice that we have actions to perform on the on state. So we're going to exit that state. We're going to perform all the exit actions. In this case, it indicates we should turn off the light switch. We're going to see a click. Then we're going to cross that transition. At this point in time, we are kind of an indeterminate state. We are neither in the on state or the off state. And this should be basically instantaneous. Then we start entering the off state. And then we notice there are some entry actions, but the off state doesn't really do anything, so we just kind of bypass that. We've entered the off state, and now we can say we are in the off state, and then the off gets all the events that are passed to the state machine. Similarly, if we get the turn on event, we see there's a transition outward to the on. We select that. We exit the off state. In this case, there's no actions to perform. Cross the turn off transition. Enter the turn on transition, and then we see there are actions to perform to turn on the light switch again. And then we're back into the on state. The cool thing about modeling active state things is you should be able to handle any event you pass at it without barfing. So in this case, we're in the on state, and we get the turn on request. Well, since we're in the already on state, we can choose to ignore it. Other times, we may choose to have a self-transition. And a self-transition means we would exit the on state and go back into it. And that may be appropriate for things like flickering or browser refreshes. Part of intelligence is contextually appropriate behavior. So in this case, we have a single event used twice, one from the on state to the off state, and one from the off state to the on state. And the same event passed the system. We could have a button that just sends out the event toggle, would switch that thing back and forth. So here we get it in the on state, cross over to the off state. The off state's active. It gets the toggle event. It goes back to the on state. States are not always about transitions. So here we have requests being passed into it, the awake and the asleep state. And in the awake state, we get a responsive yes. And in the asleep state, we get a responsive sleeping. We can ask a second question, are you hungry? And the awake state would respond back, yeah, I'm hungry for an apple. And the asleep state might have the same default response. Now, getting into implementation approaches, we have basically these variable scopes for storing state. We have the top-level packages, classes, namespace, functions, and variables. And the majority of the state that we handle in developing applications is in variables. So doing something very simple might be is awake as a Boolean value, and we have go to sleep, which sets that to false. And then responding backward, we introspect that state and then bubble up either yes or sleeping. We might decide that two states isn't enough, so we might start using either integers or strings and setting it to like a static const and then having a switch statement which determines what response to send back. We can also use namespaces for storing state. In this case, namespaces are similar to public or private. They kind of control the context when a function is visible. And similarly, when we call wake up, or use the active namespace of wake. And anytime we call the on are you awake request, it gets the current namespace value. And Samuel has a good blog on this in the very bottom of this. We can also use classes for storing state. In this case, we create a new reference, a new class called awake state and a sleep state, which has a fairly standard API, depending on what we need to do. And when we request it, we just kind of delegate it or pass it on to the state implementer. Real-world applications have very complex life cycles. When you start getting into parsers or game maps or initialization of applications or components, you start getting into very complex state transition diagrams quickly. When you start managing topology manually, like codifying everything and then every transition by hand, and it gets very difficult to maintain. It's easy to break. And typically, when you're dealing with interactive applications, you don't always know the information up front, so things change on your feet. The traditional state design pattern is very much like plugs into an outlet. You typically have one plug at any given point in time. There's not any of the actions that are kind of coded into the traditional state pattern, and I find that the transitions are fairly brittle because you're also specifying that by hand. Since you're using classes, if you have a very complicated system, you end up having a lot of pollution, a lot of classes going all over the place. And I find it very difficult to figure out what the behavior of the system is because you can't really tell what state is related to what. This gets into the need for state machines. State machines kind of abstract away the details of how you manage the states and transitions and the actions for them. You'll find often that when you're developing these things, you spend a lot of time coding the actual transition logic, and if you use an engine to take care of that for you, you can focus on the business logic instead of the transitions. This gets into Cogs. This is a library I've developed. It's a state machine library and a set of patterns that people can kind of pattern extend off of. It's named Cogs for the tiny teeth that compose the gears that keep engines in sync. And if you can imagine, we strip away all the cogs in the world, we'd be stuck with wind power. Wouldn't be able to get, you couldn't drive your car to work typically. And Cogs is also short for cognition, the meshing of neurons that would make up how we think. Cogs has a finite state machine, which is basically a single level flat state machine, and it has a hierarchical finite state machine, which allows you to nest states. In addition, they all conform to the state design patterns. You can kind of mix and match to create different abstraction layers. And there's a few design patterns I'm trying to collect inside of this library. I'll cover a little bit more. And its primary use is in components and applications and games. I develop kids' games and components for working with games. It's open source. It's MIT licensed. It's all hosted on Google, so people can play with it. It's fairly lightweight. It's only 7 kilobytes for the finite state machine and 15 for the hierarchical state machine. And that hasn't really been size optimized yet. We're still developing on things. It's pure ActionScript 3, so it can be used with Flex, Error, or Flash. It's still in beta. There's some things we're going to try to add, but the core functionality is complete. And it's part of a framework which has other useful features. When you're using Cogs in your own project, it allows you to do things like ask it where you are or what you can do. In particular, since every state deals with a period of time, you can deal with asynchronous behavior gracefully. You can eliminate the manually coding of chains of reaction, those actions, if you specify it in the state machine. You can easily inherit behavior and reduce the housekeeping. When using Cogs with interacting with other components or other services, you can map their behavior. So, for example, on the bottom, we have this black box generator, which is producing a string of characters. And on the top, we have our class, which is trying to understand where it's going, what it's doing. We have a state machine which notices that we use the exclamation point 2 different ways. And based on the state topology, we've figured out that sometimes it means something, it means different things at different times. You can bubble that up to the user as well. So sometimes you don't, like an error or, for example, in NetStream, there's a lot of connection. There's a lot of things like buffering, which made the same event can be generated at different times to indicate to the user what's going on so they're not confused about things. And if necessary, hit refresh or pause or what. Cogs uses functions for managing state. This is smaller than using classes. There's less overhead. I find it much easier to code. So this is a very simple example. This isn't exactly how Cogs work, but we have a variable called curState, which is actually a function variable, and we're passing in a reference to the function below it called sawake. I preface things with s underscore to indicate they are state functions rather than generic functions. And then we have a case statement which has some constant values that indicate what event it should be handling. In this case, we have a Cog event, which is a generic event. And the signal is similar to the type that you have in most standard events. The difference is we're using static references, so it actually uses identity comparison rather than value references. So the comparison or routing it to the correct state is very, very fast. Yeah?
Maybe you're going to get into it, but so for every state, you'd have a function declared like s underscore awake, and it would be a case statement or a switch statement with cases that are the same but with different implementations within.
No, actually, what you're seeing underneath the state are the different events that it can handle. So you're correct, and then we have a function which means that every state has a function that matches to it. Did that answer your question?
Yeah.
Okay. There are pre-built, I mentioned earlier, there's actions that are performed inside of the state machine engine. So here we have the ones that are built into Cogs. We have the enter actions, the enter. We have the exit actions at the very bottom. We have a callback and a pulse. So the callback is actually something that you can set up as a single-time callback or repeatedly, depending on how you want to do it. But typically it's designed to have one single callback after you enter the state if you want to do something. Like in this case, we're awake, we're going to perform the interactions, we open up our eyes, we start a pulse, which controls our breathing, and we set a callback in 50 seconds to yawn once. We also have those 2 other events, which are kind of, are you hungry or are you awake, and our appropriate response. As we were to exit the state, it would call the exit action. In this case, it would say eyes close, and possibly breathing starts slow. Since we're based on functions, we're still operating inside of the context of a class, and that allows us to do some kind of cool things. This is actually an example of hierarchical states. In this case, we have at the very end, if it's not handled, a return to the parent state by another function, which is called salive. We can also have return the super state, and how it responds to the states. This allows you to create templates of behavior, one in the parent class that has some pattern that you're interested in using, and then extend that. So here we have a day in the life of Joe. Joe has a very simple life. He goes to work, and he goes at home when it turns night. So looking at a simple finite state machine, you have two states and two transitions. In Joe's real life, there's actually the time to drive on the transition, but we're not really that interested in that, so we're going to just remove them from the diagram. But we find he doesn't actually stand in home in the doorway. We're more interested in what he does inside, so we open it up and we see he actually goes to bed and he goes to his desk. This starts getting into hierarchical states. Hierarchical states override the default behavior. There's certain things you do in bed that you don't do in your home, or other places in your home at least. Also, you notice that we have default transitions inside of the state machine. So when he goes to work, he's going to end up at his desk. He's not going to sit there in the front door at his office, so it would look really weird. Similarly, we have a root state, which if things can't be handled inside the state machine, they get consumed by the root state. All these states are currently inactive, meaning that none of these are, when we're first entering this world, they're all inactive. They're not receiving events. In addition, the state machine itself has a state, because it hasn't been turned on yet. So it too rejects any of the events passed to it. We still have the pseudostates, and those are going to be our start and exit points. In this case, we're turning on the state machine by a call in its state machine, and it takes the first transition, and it calls the interactions for at home. That might be unlock the door, open the door, enter the house. At this point, we're at home, but the in-bed state is inactive. We might see there's an initial transition to perform in the at-home state, so we would find that, activate that, and enter the in-bed state. Now the state machine is determined that they're at the top state that it needs to. It opens up the doors for business, and it's responsive to external events. At this point in time, we have two different stacks. We have an inactive stack and an active stack. And we denote that the in-bed is actually active and current, and then we also have the at-home is also active. So all the events in both in-bed and at-home are still active at once. If the in-bed can't handle it, it passes up to the parent at-home state, and it would handle it. So, for example, if the phone rang in the bedroom, you might override the behavior by getting in the one that's by the bedstand. But if the doorbell rang, you would still be able to access that from at home. This can be true for however high, and you can even have nested states, in addition to the however that are not active at home. As I mentioned, that there's a current state which overrides the parent's behavior. Events inside of Cogs are very similar to a slinky. They start from the top state, and they kind of work their way down until the root state. Any point in time, they have a chance to be consumed. In addition, we have behavioral inheritance. They can walk down that state, but they also walk up and down the class hierarchy. So, for example, we have a closet, which extends from doored space, which extends from 3D box. The real power of Cogs comes in when you're dealing with transitions. So here's a simple transition in a flat state machine, going from home to work. We turn on the hierarchical states. We start seeing that we have an in-bed and at-desk again. But that transition is still affiliated with the at-home and at-work. We can almost slice this into two different layers and not abstract away the details. We notice that the in-bed is the current and the active state, so this is the one that's getting all the events. And our target state is the one that's specified at the end of the transition, so the at-work state. We're not actually specifying at-desk. The result target state is what's going to happen after the end of this transition, because we have a default action to perform, or default initialization. Cogs handles transitions in three basic phases. One, there's a path discovery. There's a second, is it executes all the actions it's kind of collected along the way. Then it caches that routing later in case if you want to, because the path discovery can be fairly expensive depending on how complicated your topology is. So here we have the act of routing from the currently active state down to the state that requested the transition. And remember, this can be however tall. Then we collect the actions going from the first state to the second state. And then we collect the actions going from that state to whatever the last, these default initial transitions. And that can be however tall. So once we have all these actions, it's very similar to SQL transactions. We perform them all as once as we can. And after we performed all these actions, we set the last state to current. So from Joe's perspective, the actions might be, when you're going from bed to going to work, you might leave the bed, make the bed, exit the house, lock the door, cross the street, enter the building, unlock the building, enter his office, open his PC, and start working. The Cogs engine takes care of the actions, all that list, without you having to specify the order of their execution. You just affiliate them with the state, either the enter or the exit, and then call the transition. Once you have entered a state, there are events broadcast, so other people can keep in sync. So for example, Joe has his own set of internal state machine. He's either working or he's sleeping. So once we detect we're at work or we're at home, he does a state transition for himself. And you can also determine what state at any point in time Joe or the work is in by asking, is it in the state, and passing in a reference to that state function. These are the transitions supported by the finite state machine. You have a self transition and a sibling transition. You can kind of assemble these as much as you want into however complex. Hierarchical states get much more complicated. You have arbitrary depths and arbitrary kind of siblings. This is the test case, which is available. You can see the link to the source code in the bottom, which represents all the different transitions that are possible. Look at one of the states. In this case, S11 is kind of the default context we're operating from. So you can see the interactions. We might transition or trigger the UI to update which state is visible. We have the exit as well. There's something that happens on the enter and exit actions that are really interesting, except from the UI perspective. We have the initial transition, which says that when we're in this state, to transition to the next parent state, or actually this one. We have the name transitions, which there's two different ways to transition inside, or actually there's three different ways inside of Cogs. Tran, which is mentioned here, is an immediate transition. And unfortunately in Flash, we were dealing with a mostly single-threaded model. So what would happen is it would transition that state, but continue to perform the functions which the script it handles afterwards. So what request transition does is it queues up the transition requests and then processes them in order. And you can use that queued request to do some pretty interesting things as well. If, by default, there are initial transitions performed past that state that's requested, in this case, we've asked to go to state S11, which is this one. In that case, it doesn't have any default transitions. If you can also choose not to bypass. You go directly to a particular state. And that's useful for deep linking on things. Common life cycles in some of the applications. This is a player that I work on. It's a company called KidThing. We make some really cool children's educational games. If you have kids, I definitely recommend you check them out. There's a lot of different design patterns we use inside of this from a state model. One of the simplest is online, offline. We have the ability to go to a store and also say the ability to connect to other users. So here's just kind of a common state model for dealing with that. The interesting thing is we have connecting and a disconnecting, and there's transitions between that. You can imagine that you are saving files or opening up. In our case, we're downloading files, saving that where the progress is, but maybe it's a flunky network connection at a cafe, so maybe the connection reestablishes itself. Setting up the actions appropriately lets you handle any of those cases fairly easily. We also notice that there's a different, we have the same event being used at different times to do the correct behavior. For example, the network on both lets us take it from an offline to a connecting state, as well from a disconnecting back to the connecting state. We have a lot of things which follow this kind of basic life cycle of unloaded, loading, loaded, and back to unloading again. Using Cogs, there's an extension to Cogs called Chain, which lets you kind of, especially in ActionScript 3 projects, kind of set up workflows similar to a command model. And there's basically, you can create this tree of sequential or parallel tasks for it to deal with. In this case, we're dealing with a sequential task. So inside of that loading, we've created a task list for it that says load configuration, then start loading the game engines. And when you've loaded engine 1, go to loading engine 2. You can see an example of how this works in the bottom. What's interesting about the way Chain works is you can start the loaded config doesn't know what engine is going to have inside of that text, but you can extend that chain as much as you want. And then from the perspective of the top level state, it's not going to go to the loaded state until all the tasks inside of the chain are finished. Similarly, we can do that with a parallel task. In this case, we've even extended that sequential chain even further. The engine itself has a loaded engine configuration, has a parsing configuration task, and then we have a bunch of assets which represent photographs. We don't really care what order they happen in. We just want to make sure they all are loaded before we go to the loaded state, and then propagate that back up until we, to the very, very parent, this state. You can see this, the syntax is very similar. We're just making the factory function is just using a parallel worker versus a sequential worker. One of the things that Cogs does is introspect the functions that are available to create the topology, so you can kind of see visually that your states are actually well formed. So it doesn't support cycles, it doesn't support things that are outside of the root. So this gives you kind of an XML-based view of what your function hierarchy looks like. This is the life cycle of a piece of content. And there's an unloaded state, and any piece of content plays for a certain period of time. And it may be timeline-based, it may be like a video, or maybe a video game, which has some arbitrary limits. But these are generally for a piece of like a video, the state that it exists at any given point in time. And there's actions affiliated to that, which communicate to the player what UI and what user participation can be. So for example, there's two different behaviors that you find when you're working with media players. One of them is the auto start feature. So if you think about YouTube, you have the capability when you go to the YouTube site, if you go directly to the video, it automatically starts playing. But if you see that same YouTube video embedded into a person's blog, you'll find that the page doesn't start playing until you actually request it. I'm sure they use the same player for both things. They just pass in a different flash variable. Similarly for this, you can pass in at the right bottom, you can see that once we've hit the loading state, look at that value that's been passed in, say as a root variable, and determine what to do. In this case, we're dealing with a timeline piece of content. It starts to play. But it could be the same thing for an FLV. Similarly, with actions performed when we've reached a certain percentage of the playing. In this case, whether we should go back to the beginning and auto-rewind. Think of YouTube again, where you have, at the very end, it pops up a dialogue that says, would you like to play this again? Send this to a friend. Or if you're working with VHSs, you don't want to rewind. You have to rewind it before you get back to the store, otherwise they'll charge you for it. One of the cool things about modeling things in states is you can do what I call introspecting them to develop the UI. So there's a special feature inside of Cogs which is get options. And it basically looks at that entire stack of what's active. In this case, we have it in the middle of the stopped, of the loaded, and collects all the actions that can be performed. In this case, it's arbitrary because your application will have to figure out how to codify them. We have the rewind and stop, the seek to, and the play and clip, and then we choose to propagate that up to the view and enable or disable the buttons depending on that. And that would change based on the state machine changing underneath it to update the UI in a similar fashion. When you're going over playlists, you have this basic topology of there's nothing inside. It has items, one item or multiple items. And then on the right here, or the middle, we have the collection of just two simple state machines about, like toggles, which one, where we are at. And this controls what events you pass to the user, as well as in the right-hand side, what UI you expose as far as, can they go to a clip? Is there a next clip available? They can go backwards or forwards or backwards. In conclusion, I hope that I've shown you some of the terminology you can use to describe state when you're working inside of teams, and how to construct some of these things inside of a hierarchical topology. Some of the other aspects of the TORWORK framework is using this to do asynchronous testing. If you're dealing with any type of testing of network stuff or unit tests which have a lot of data, this is a useful way of doing things. And it operates as similar as I showed you with chain. We have a very small tuning class, which if you're doing any type of banner ads or very small ads on the web, it's useful. And Tweenie, which extends that kind of playhead model for dealing with FLVs and MP3s. Some of the features that are in development are a graphical admin tool, which kind of takes the UI that I've shown you here and then lets you see what's happening on the state machine in real time. Persisting states is an AMF, so you could actually serialize them to the web or between clients. Rollbackable transactions, so you could take a transition and then transition to another state and then undo that. A graph-based state machine, which allows you to create node-link type structures and then actually await those. Because when you're transitioning, typically transitions, when we're thinking about from a Flex's perspective, they actually do take time. But sometimes when you're routing things, you want to be able to route between two different points to include those non-zero duration-based transitions. And also a fuzzy state machine, which deals with overlapping state topologies. I'm also collecting a library of life cycles to both codified and Cogs to cover some of the common design interaction patterns, because people tend to reinvent them over and over again. This is similar to traditional design patterns, but just in the interactive space. And if you have any particular patterns that you would like to see, or you have ideas for states that you use in your own, please feel free to send me yours. There's some good books on using state machines. Mirosumix is how I was inspired to write Cogs. He's really targeting C and C++ for embedded devices like GPS. Jonathan Kay wrote a book a few years ago on how to do it in Flash MX, but the book is still relevant other than the actual code is written in ActionScript 2. And Sam has a good presentation on how to use various approaches to implementing state other than state machines. So for more information, you can go to code.google.troyworks to get the actual source, unit tests, and examples. You can follow some of the development Cogs, including this presentation, at troyworks.com/cogs. You can contact me at troy@troyworks.com, any suggestions that you'd like to see, and that's it. Any questions? Yeah?
What are some uses for a state machine? What are some applications that have complex states besides games?
Besides games? Think of a website. If you're having any type of tiered navigation, if you want to go from the home page, which has maybe 3 different tiers beneath that, to another part of the site, which has 3 different tiers between that, you just specify where you want to go. So again, so you have a button that says, or example, if you click on the About Us page or something like that, it would exit out of those nested tiers, cross that into the other section of the site, and enter that as many levels deep as you want to go to. And that's true for most applications. You can think of any type of hierarchy you can map onto a state machine very easily. What's that?
Parsing event streams.
Yeah. Yeah, parsing event streams and parsing in general. Like, for example, we were doing a streaming media player, and the events coming off of the net connection, it was a Flash media server. It was really hard to figure out what to present to the user, because we're trying to synchronize a bunch of images to this underlying stream, which is just sending out events like crazy, depending if it's buffering or it's not buffering, and how to pause the synchronization of the image show and the text show based on what was happening with the FLVs being kind of the sync track. And the state machine was the only way to really kind of accomplish that, because it says it passes out the same events, but it means completely different things on that. And the W doesn't really publish a lot of these documents on how these things actually, the underlying state machine, you have to kind of figure it out, which is one of the reasons why I'm trying to get libraries of understanding the behavior of these common elements we have to deal with on a day-to-day basis, programming-wise.
Historically, state machines have been very powerful, but somewhat tricky to design. I'm wondering if you're working on any tooling or know of any tooling that could be used to help get a particular Cogs design to actually be what... I'm sorry, could you speak up? It's kind of hard to hear.
I'll repeat the question for you.
Historically, state machines are pretty powerful, but also they're hard to get right in particular applications. So people have, sometimes have graphical editors for getting a particular set of state machines under transitions, and they're allowed, event handlers and all right. So I'm wondering what sort of tooling you might know.
That's something that we're working on. There's not a whole lot out there. In fact, especially for dealing with hierarchical states, most of the stuff that's out there is really, really tailored to C++ and other very sophisticated languages. And they're not, ideally in an ideal world, you want to have something as an Eclipse plugin which can start either generating the code or round trip it. And it's not that hard to do, it just time-wise for me to spend the time doing it. And it's not that much code to write overall, because you're dealing with functions rather than classes, so it's not that hard to change the topology. And typically what happens for me is, the reasons I develop Cogs is I do a lot of prototyping for people. I have to deal with things in very, very quick schedules. So you come up with a very simple topology, and you evolve it over a period of time. And because you're dealing with things over, you're segmenting the application behavior into very small chunks, it becomes very easy to start reparenting states or extending the states, adding new events and copying things around, where if you have a monolithic procedural class code, it becomes very difficult to at that point in time, to break it apart in different areas. And this comes in really handy like when you're doing like debugging of applications. If you want to stop it from going to another particular state, you snip it at the end of the loading thing. It never goes on to the other state. You can stop it at the very initialization area, figure out what part of your configuration file isn't working.
So you were talking about reparenting states as a design progressed, so you would actually take a subclass that represents one nested state machine, and then you would change its superclass?
Not just that, but inside of the class itself. You can start that topology. They're all function pointers. You just change the order that they're pointing in. Like, for example, going back to, where's my mouse? Initially here, we might have, we're interested we go to add desk, and then realize, oh, that's actually in a larger context of work. It's not that hard to add another function that says at work then change the parent of that desk pointing to that. So you can reparent things at the top or extend it from the bottom, either direction. So at the desk, we might say there's answering the phone. And at work, it might be in the Atlanta area or something like that. There's a lot of different ways we can extend it. And since it's just writing a function, it's not that much overhead. Yeah?
Is the intention in the state machine to define everything that differentiates, say, an object and the transition that it goes through so that it's entirely described by the state chain? So, for example, if you had an object whose values were changing, would you have the values before, values after, and is it necessarily all described in the state chain?
It's not. It depends on your application. In some cases, you try to choose of those contexts that are available the appropriate way to store things. And in some cases like that, you're dealing with just the state, a variable. The variable makes sense to just do it. You may have a last variable and a current variable. But if that gets more complex, if there's actions to perform when that thing changes, it becomes more useful to have a state machine because you start thinking about there's enter actions, and there's exit actions, and there's pulse actions to do that. It's really dependent on your application. There's some times where, say, a variable works perfectly fine, but I find that as you evolve, like when I'm doing fast prototyping, I don't always use Cogs initially. But as the application gets more robust, you start figuring out all these complications in state, like self-transitions, and that you want the behavior starts to become more of an intelligent creature. You start having to protect itself from any errant events because, say, well-designed topology, you should be able to toss any event into the system and not have it perform something you don't expect. Any other questions? Yeah.
Is there a way to describe the states? You mentioned state chart. Do you do a state chart before you do the
Yeah. Yeah, I do typically. A lot of times it doesn't have to be as involved. The most important thing is that your actual code works, right? So anything that gets close to that, I find that state charts are really useful because like you're working in a white. People have the common terminology. People use boxes and arrows. There's different ways to describe it. When we do fast prototyping, what we end up doing is we have a whiteboard session where we have a state, and we're not always constructing the entire state topology. It's a map of a particular area, like a user logging in, that might be added to an existing application. And on top of that, we start having the UI aspects of it and the underlying data model changes that have to happen with those state changes. And it becomes easy at that point in time to create a physical prototype of just that model. If we want to validate that interaction, you think about Pac-Man, you've got to make sure the game end state is there. And as you hit the game end state, how do you get back to the beginning to replay the game? Those kind of things don't typically show up unless you're actually playing with the actual interaction, especially when you're dealing with clients who are non-technical. They don't know what they want until they actually see it. And you show them comps, they're going to get confused. They're not going to be able to get the interactive aspects for it. Any other questions? Yeah?
Let's suppose you build an application for a bunch of components. And each component has some of the states within that component at a time. Do you think that technical advice was the best way to deal with application states and component states?
Well, it depends on the complexity of the component. So, for example, the earlier example I was using of synchronizing a bunch of images and text transitions to an underlying streaming FLV. So, in that case, what we did is there's a whole state machine inside of the Flash player which deals with how to consume FLV that's coming in from the network and exposing that. And it sends off events at different points in time, like it's entered buffering or it started streaming. You can see the buffer fill or empty depending on what's going on. So in that case, we created kind of a wrapper for what was going on to the FLV based on lots of testing in the real world, and then our application built on top of that. So that's one way of doing it. That's typically how I do it for more complicated things because then it becomes much easier because in some cases, your application is going to do different things based on the underlying topology. So for example, on a media player, you might have just a play pause button, but on a full transport control, you might have record and replay and seek. There's different levels of detail exposed to the user. So the fidelity of your state machine model may be different depending on what you need. Any other questions? Yeah?
Do you have sample source code, or could you explain how to use the interface to the Cogs API?
Inside of the actual, if you go to code.google, let me get to my code environment. So inside of the code base, there is com.troyworks core.cogs, which has all the basic classes, in particular finite state machine, FSM, and hierarchical state machine, HSM. Some of the interfaces they kind of are built out of. And if you go into the example or the test project, there is the test case I showed you, which is the 8-state machine, which has all the different static signals that we're using to route on. How you construct it, and this initial state is how we're determining what of those various states we're going to end up at. And we have a bunch of utility methods which allow us to deep link to that because we don't want to type in the values all the time. We have some utility methods to help fire off events. And we have a particular typed 8-state machine event. We have a few utility methods to determine what state is currently active, or if it's, that means the very top one, and if it's active at all. And this is the state machine itself. This is our initial transition where there's a special signature which determines what our parent state is. In this case, this is our root state. It's built into Cogs. This is our first state, S0. Since we get to higher states, this is our state 1, which is nested inside of S0. We just noticed that its parent state, we note a note here. And you can see if I wanted to change this hierarchy, I just change this value, and it's pointing to another state. And to actually...
So he's going to ask, how do you make the transition safe? When you refer to it being safe versus immediate?
Well, what we're doing in that case is we have basically it's a heartbeat, which is listening to an event. And all events that are passed in through the transition, this request transition, add into a queue, and then it's just pulling off the bottom of the queue. Because we can't do that in a single-threaded model without any, with any surety about that. There are times you can use that to do mementos, like sometime point later, add something to the top of that stack, and we'll get to it eventually. So that's the way we currently handle it. And if you wanted to, this is the test case for a simple 2-state like light switch. One of the advantages of using a finite state machine versus the hierarchical state machine is you can return values. So if you're actually doing text parsing, you can kind of you go through the state machine at different times and then return the appropriate node. And to actually test it, this is the unit test, which has all the different test cases which I covered in So this is the graphical version of this test case. This is represented inside this class itself. This is how we're kicking off each one of them. And this is built off of the asynchronous testing library. So here we're using introspection on the testing library to look through this function. This starts up the test. The A test means it's an asynchronous test. At some point in time, we have a timeout variable, which says at this point in time, if the test hasn't returned back the appropriate value, it fails the actual test. Goes through the test, sets it up, says checks at the result whether the state machine is active. It looks at the transition log, making sure that it actually has the enter and exit events at the appropriate spaces. So that's a very simple one. We'll look at a more complicated one. So here you can see this long string of, let me open this up full. These are the order of events that happen. This is the last one. It's going backwards and forward. So exiting state 11, exiting state 1, entering state 1, entering state 1, 1. Does that answer your question? All right, any other questions? Well, thank you guys for coming, and